This video is about moving in a vertical circle. Imagine that we have a stone attached to a string. First, we move this stone at constant speed in a horizontal circle. Since speed is constant, there is a constant centripetal force pointing towards the center of the circle. Since the stone is moving in a horizontal circle, the centripetal force is provided by the tension in the string. At every point around the circle, the centripetal force is simply equal to the tension. The situation is a bit more complicated when we start moving the stone in a vertical circle. Let's examine this situation in more detail. The stone is moving in this circle. We'll examine the forces at 4 different points along the circle. Since the stone is moving at constant speed, the centripetal force is constant. The centripetal force points towards the center of the circle. Let's draw this force at each point. So what force or forces provide this centripetal force? Let's examine what happens at each point. No matter where the stone is, the gravitational force always acts on it. This force is pointing downwards. The other force that acts on the stone is the tension in the string. The key here is that at any point along the circle, the centripetal force is the vector sum of the tension and the component of the gravitational force that is pointing towards the center of the circle. So let's figure out the tension at points A, B, C, and D. Point A is at the top of the circle. Here, the gravitational force is pointing towards the center of the circle, so it is contributing to the centripetal force. Therefore, the tension here is smaller compared to all other points around the circle and can be drawn like this. Therefore, at point A, the magnitude of the centripetal force is equal to the magnitude of the tension plus the magnitude of the gravitational force. At points B and C, the centripetal force is horizontal, and as usual, the gravitational force is pointing vertically downwards. So at these points, the gravitational force does not contribute at all to the centripetal force. Therefore, the tension in the string is equal to the centripetal force and can be drawn like this. Just a quick reminder here, before things get too confusing, that what we have here is not a free body diagram for the stone, because a free body diagram would not include the centripetal force, since the centripetal force is the resultant or net force that acts on the stone. So as we said, at points B and C, the centripetal force is simply equal to the tension. Finally, let's examine point D, which is at the bottom of the circle. Since here the centripetal force is pointing upwards and the gravitational force is pointing downwards, in a way we can say that the gravitational force is working against the tension. The tension is the largest at this point and can be drawn like this. So we can write that at point D, the centripetal force is equal to the tension minus the gravitational force. Based on this example, we can also conclude that the higher up the stone is along the circle, the lower the tension is in the string. This wraps up our discussion about moving in a vertical circle and completes the final video of subtopic 6.1. In the first video of subtopic 6.2, we learned about Newton's law of gravitation.